Hello and welcome to this lesson for OCR A-Level Physics, Module 5, the Newtonian World and Astrophysics, looking at the module of oscillations and the topic of dampening. So if we've been successful and we've learned in today's lesson, we should be able to define and describe a forced and freely oscillating system, describe and define a damped oscillating system, and detail the different types of dampening found on systems. So we're going to be looking at the following part of the OCR A-Level Physics specification, 5.3.3 Dampening. Now in previous lessons we've covered oscillations in several different oscillating systems. Now these include mass spring oscillators. So here you can see the mass spring moves in a periodic fashion. It exhibits a simple harmonic motion. So an oscillating system with simple harmonic motion is one where the displacement of the oscillator is proportional to the acceleration of the oscillator in the opposite direction, or A is proportional to negative x. Now we can categorize all oscillating or vibrating systems into two different types. So there are two main types. The first one is free oscillators. Now these are oscillators which oscillate freely after being initially disturbed. So a swing is an example of a free oscillator. Now these systems are which ones that oscillate naturally. So these include systems that must be disturbed initially but then do not need a further force. So free oscillators only require an initial force. So if no external forces are applied to the system after it starts vibrating, it is a free oscillator. Now free vibrations involve no transfer of energy into or out of the mechanical system. So in this system no energy is transferred to the surroundings. System 2 is a forced oscillator. These are objects which have their oscillation produced when a driving force is placed on it. So a signal generator is an example of a forced oscillator. So a forced vibration is caused by a periodic driving force acting on the system. This periodic driving force causes work to be done into the system. So these are systems which always need a force to cause them to oscillate. These systems need to be driven constantly to cause them to oscillate back and forth. The force cause of this movement is called the driving force. So if a force is continually or repeatedly applied to keep the oscillation going, it is what we call a forced oscillator. So we know that there must be a periodic driving force. So consider a pendulum or mass spring system. They will oscillate after initial force is placed upon them. It does not need a constant force acting upon them to produce the movement after the initial force. If an oscillator is set into motion and has no periodic force acting on it, then it is described as a free oscillator. So a simple pendulum is an example of a free oscillator. It will continue to oscillate freely after it is being displaced. So once the initial force has been taken, the oscillator will still oscillate. Now a free oscillator produces free oscillations, defined as where a system is given an initial displacement and allowed to oscillate or vibrate freely. So a free oscillator system will oscillate at a set frequency called the natural frequency. So here we can see our pendulum vibrating at its natural frequency. The factors which affect the natural frequency are the terms in the equations used to calculate the time period of that oscillator. Now when an oscillator is oscillating as a free vibrator, there is ideally no energy put into or taken out of the oscillating system. So this assumes there is no dampening forces such as air resistance in the system. Whilst a forced oscillator has a periodic driving force acting on it, affecting its oscillation. This driving force is constantly acting on the system. So an example of a forced oscillator is a harmonic oscillator. They tend to have a motor driving the oscillation. So forced oscillators or vibrators can only be produced when a periodic driving force acts on the object. So the periodic driving force is placing energy or doing work into the oscillating system. So oscillators can be forced to behave in a different way to their natural motion. If, as a pendulum is swung one way, you were to push it in the opposite direction, it would turn back. So this action turns a free oscillator into a forced oscillator. This is a very energetic activity to do. It requires a lot of work to be done to achieve this. It is more efficient to allow a system to oscillate at its natural frequency. Repeated applications of forces from your hand in different directions can force a pendulum to oscillate at a different frequency. This would be a forced oscillation, and the frequency you were causing it to swing at would be the driving frequency. So forcing oscillating systems to not oscillate at its natural frequency involves adding energy to the system while it oscillates. If a system is not oscillating at its natural frequency, it is unlikely to undergo simple harmonic motion and will dissipate energy quickly. This is why a forced oscillator needs to maintain a constant driving force to maintain its frequency. It's much easier to let an oscillating system oscillate at its natural frequency than drive it. Now, many oscillating systems, such as piano strings, can be forced to oscillate, but oscillate best at their natural frequency. The driving force puts energy into the system at a certain frequency, not necessarily the same as the natural frequency of the system. The natural frequency is the frequency in which a system would oscillate if there was no driving or dampening force. Now, many oscillating objects, such as yo-yos, can be forced to oscillate, but oscillate best at their natural frequency. If a yo-yo is allowed to hang freely and move up and down naturally, it's carrying out a free vibration. It's vibrating at its natural frequency. If a yo-yo is made to vibrate by a periodic driving force of moving your finger up and down, the yo-yo is carrying out a forced vibration. The frequency of the oscillation is the driving frequency. If the driving frequency produces a driving force produces a driving frequency, which is the same as the natural frequency, then the amplitude of the oscillation is at its largest. So, free oscillations involve no transfer of energy to or from the surroundings. These are natural oscillations once a system has been displaced from equilibrium, and the system oscillates at its natural frequency. Forced oscillations involve energy transfers into the system from a periodic driver, oscillations in a system due to a periodic driving force, and the system oscillates at its driven frequency. So an object which is freely oscillating is observed to dissipate energy to the internal energy of the surroundings. So if a system is performing simple harmonic motion at its natural frequency, it will dissipate energy through a friction force on the system. So in this example, friction causes energy in the simple harmonic system to transfer to the internal energy of the surroundings, and air resistance causes energy in the simple harmonic system to transfer to the energy to the internal energy of the surroundings. Now, if a pendulum is left to swing without interference, its amplitude will decrease with each swing owing to its air resistance and internal stresses due to the flexing of the material of the string. Now, although the amplitude decreases, the period for one oscillation remains constant throughout. The forces which reduce the motion of the oscillator and dissipate energy are called dampening forces. These frictional forces oppose the motion of the oscillating body. They slow or simply stop simple harmonic motion from occurring. So the effect of an oscillating system decreases in amplitude due to losing energy from the simple harmonic motion system to the surroundings, and that is called dampening. So dampening forces are resultant forces which cause work to be done from an oscillating system to the surroundings. Now, we know that another name for dampening forces is dissipative forces. Now, this is because the dampening forces dissipate energy into the surroundings. Now, energy is transferred from the mechanical system to the internal energy of the surroundings. These forces make our system an open system. Now, systems are often deliberately damped to stop them oscillating or to minimize the effect of resonance. Now, parts of systems which are designed to produce dampening forces are called dampeners. So here are some examples of car dampeners found on the wheels of cars. Now, the dampening types are classified by the effect that they have on the oscillating motion of the system. Now, the amount of dampening can vary, and this can determine its effect on the vibration of the system. There are 4 different types of dampening. The first type is underdampening or light dampening. This is dampening that slowly reduces the amplitude of the oscillations but keeps the time period and frequency almost constant. So in this type of dampening, the oscillator continues to oscillate back and forth, the amplitude decreases each time, but the frequency stays the same. In real terms, the oscillator decreases in swinging over time. Most types of oscillators in the real world have light dampening. Now, we know that basically, in real terms, the oscillator decreases in swinging over time. So we can say that the dampening effect here is very gradual, that the amount of the amplitude changes each time is very small. So we can see that straight away. Now, many systems are underdamped and oscillate whilst their amplitude decreases exponentially, such as the mass oscillating on a spring. So the dampening might be quite small, but eventually the mass comes to rest. Now, examples of light dampening include the simple pendulum and the mass spring system. The second type is heavy dampening. This is dampening that reduces the amplitude of oscillations but keeps the time period and frequency almost constant. In this type of dampening, the oscillator continues to oscillate back and forth and the amplitude decreases each time, but the frequency stays the same. In real terms, the oscillator decreases in swinging over time. Now here, the dampening effect is quite fast. Heavy dampening is the same as light dampening, except it takes less time to stop oscillating. So it is the same as light dampening, except the reduction in amplitude is greater. Now examples of heavy dampening include the simple pendulum and the mass spring system. However, the resistive forces will be increased by using objects with larger surface areas, as this would increase their air resistance. The third type is called critical dampening or very heavy dampening. This is when an oscillator returns to its equilibrium position in the quickest possible time without going past the equilibrium position. So in this type of dampening, the oscillator returns to equilibrium without making one oscillation over as quickly as possible. So in real terms, the oscillator returns to the centre after being displaced very quickly. So a critically damped oscillator returns to equilibrium position very quickly. The dampening effect here is very sudden. So a critically damped oscillator returns to equilibrium position very quickly. An example of a critically damped system is the shock absorbers in a car. It's advantageous to have the oscillations decay as fast as possible. So here the system does not oscillate but asymptotically approaches the equilibrium condition as quickly as possible. So for critical dampening, the graph has a fast decreasing gradient when the oscillator is first displaced until it reaches the x-axis. Now finally we have overdampening. This is when an oscillator returns to its equilibrium position in a very slow time, without going past that position. So in this type of dampening, the oscillator returns to equilibrium without making one oscillation over a long time period. In real terms, the oscillator returns to the centre after being displaced very slowly. So a heavily damped oscillator returns to the equilibrium position very slowly. The dampening effect here is very gradual, and it's the most dissipative dampening effect. So overdampening can be considered to be extreme critical dampening. So for overdampening, the graph has a slowly decreasing gradient from when the oscillator is first displaced until it reaches the x-axis. So we can summarise dampening as the following. There are four types of dampening. Underdampening or light dampening. Dampening that slowly reduces the amplitude of oscillations but keeps the time period and frequency almost constant. Heavy dampening. Dampening that reduces the amplitude of oscillations but keeps the time period and frequency almost constant. Critical dampening, when the oscillator returns to its equilibrium position in the quickest possible time without going past that equilibrium position. And finally, overdampening, when the oscillator returns to its equilibrium position in a very slow time without it going past that position. Now, all types of dampening reduce the amplitude of oscillation over time. Generally, the heavier the dampening, the quicker the amplitude is reduced to zero. An exception to this is overdampening. All types of dampening dissipate energy from the mechanical system to the internal energy store of the surroundings. So it's a very important key idea. Now, in the case of damped motion, the kinetic energy of the oscillator is transferred to other forms, usually heat. Now, critical dampening is often desired because such a system returns to equilibrium rapidly and remains at equilibrium as well. In addition, a constant force is applied to a critically damped system and it moves the system to a new equilibrium position in the shortest time possible without overshooting or oscillating about the new position. Now, plastic deformation of ductile materials reduces the amplitude of oscillations in periodic motion in the same way as dampening. As the material changes shape, it absorbs energy, so the oscillation becomes smaller. So that brings an end to our lesson today. Let us summarise what we've looked at. Free enforced oscillations, the effects of dampening on an oscillating system, and observed forced and damped oscillations for a range of systems. So if we've been successful and we've learned in today's lesson, we should be able to define and describe a forced and freely oscillating system, define and describe a damped oscillating system, and detail the different types of dampening found in systems. So thank you for watching this lesson on dampening, which is part of the oscillations topic in OCR A-Level Physics Module 5, the Newtonian World and Astrophysics. Thank you so much and have a lovely day.